For Unit 2, FRQ 2, Part A, it is asking us to draw a free body diagram for a sled that's represented by a dot and is sliding down a ramp at a constant speed. And then each arrow you draw is 1 point. So for Part A, I drew I drew normal force perpendicular and away from the surface. So this is 1 point. I drew force of friction. Since it is sliding down the ramp, the motion is downwards, so it's the opposite of motion. So I drew force of friction away and it's parallel to the surface. So this is another point. And then I drew the force of gravity pointing straight downwards, which is another point. So I got 3 out of 3 points for Part A. For Part B, it is asking us to starting with the Newton's second law, derive an expression for the force of friction exerted on the sled. Express your answer in terms of mu of m, mu sub s, mu sub k, and data and physical constants as appropriate. And the grading criteria for this problem is 1 point is earned for starting with Newton's second law, which I did over here and right here. And you need to also start with force of friction minus Fg sine theta, which is equal to max, which I did right here. So I got 1 point for this. The second point is earned for setting normal force equal to component of force of gravity. So right here I set normal force equal to the force of gravity, so this is another point. The third point is earned for including a component of the force of gravity with the force of friction in Newton's second law. For this problem, or for this point, I didn't get it correctly because I didn't set max equal to 0. I didn't set max equal to 0, so when I moved Fg sine to the other side, it was moved. So this force of friction is equal to max plus Fg sine, which isn't correct, and it should be at force of friction equal to Fg sine theta. So for this problem, I didn't get it correctly, but so instead the answer should be Fg sine theta minus force of friction equal to max, which is equal to 0. So when you move it to the other side, the force of friction will just equal to Fg sine theta. And for the fourth point is earned for a correct expression for the coefficient of kinetic friction. And again, I didn't do it correctly, so I didn't derive the problem correctly since I still have max in there. But in order to derive the equation correctly, here I have the force statements for the x and the y. So I'm gonna just do it assuming I did this part correctly. So the force of friction would be mu sub k times Fn equal to Fg sine theta, because it is kinetic friction because it is sliding down the ramp at a constant motion or constant speed. And since for the y we set Fn equal to Fg cosine, since the y direction doesn't move out, which means we could just put Fg cosine here, which means mu sub k times Fg cosine theta equals Fg sine theta, and you move it to the other side, so mu sub k is equal to tan theta, and that is the fourth point. So for part B, I got 2 out of 4. For part C, on the axis shown in figure 4, sketch a graph of the speed v of the sled as a function of time from t equals 0 to t equals 2t, and we were given that from t equals 0 to t equals 1, the sled slides down the ramp at a constant speed, and at t equals 1, the sled reaches the bottom of the ramp. From t1 to t2, the sled continues to slide on a horizontal surface as shown in figure 3, and the sled comes to rest at t equals 2t. So for part C, since from this is 0, from t equals 0 to t1 is sliding at constant speed, and this is a function of speed over time, it will just be horizontal since the speed doesn't change at all. And since it is coming to rest, it will be coming to 0 from t1 to t2. So it will slowly go down. And so for the grading criteria for this problem, I got 1 point for drawing a straight line over here, so this is 1 point. And another point is drawing for a line or curve that shows decreasing speed from t1 to t2, so this is another point. There's another point for a negative slope, which is a negative slope. So I got 3 out of 3 points for this problem. For part D, is asking us to indicate how the slope of the graph between t equals 0 and t equals 1 sketched in part C would change, if at all, if the angle of the ramp were increased and justified your claim. So for this, I didn't do it correctly because I said it wouldn't change at all because it has constant velocity, but it does change if the angle of the ramp was increased. So before, if the problem was like this and this is theta, and since the ramp is increasing, it would look more like this, which means that if the force of gravity is pointing straight down of the object and these are the components, the component parallel to this would increase, which means that the force, the component which adjacent to it would decrease, which means the force of accelerate, or which means that it would accelerate more, which means that instead of the speed being at constant speed, it'll be accelerating. The speed would be accelerating, which means it wouldn't be a horizontal on the graph anymore.